Picture a vehicle moving down a highway at 70 miles per hour. Suddenly, a pedestrian steps into the road. Time freezes. In this exact frozen millisecond, the vehicle's sensors are capturing a massive amount of environmental geometry. A modern autonomous vehicle generates up to 50 gigabytes of sensory data every single minute. To process that data, the car must send it to the cloud. A packet routes from the vehicle's antenna to a local cell tower, across a wide area network, and finally to a centralized data center, before the decision travels all the way back. That round trip can easily take 200 milliseconds. 200 milliseconds sounds fast, but physics dictates otherwise. At 70 miles per hour, waiting on that network routing means the car travels another 20 feet before the braking system receives the command. In physical environments where actions result in life or death consequences, relying on the transit time of centralized cloud processing is a fatal engineering liability. That single vehicle is just one node. Multiply its data output by the billions of connected devices currently coming online globally, and the current internet infrastructure begins to buckle. By 2025, the world is projected to generate 175 zettabytes of data. Pushing that volume to remote cloud servers for analysis would break global bandwidth capacities. We are running into a concept known as data gravity. The sheer mass of the information being generated is hitting the physical speed limits of light traveling over fiber optics and the hard economic limits of network bandwidth. To solve this, the architecture of the internet has to invert. Instead of sending raw data across the country to massive compute clusters, networks must bring the compute power directly to the source of the data. This localized distributed computing architecture is called edge computing. It is a necessary structural evolution of the internet required to process real-world data at the speed of physical reality. To understand how this new network architecture works, think of data processing like preparing a meal in a commercial restaurant. The traditional cloud is the off-site food warehouse. It has infinite storage capacity and heavy machinery, but if a chef has to drive across town to that warehouse for every single diced onion, real-time dinner service is impossible. Edge computing is the restaurant kitchen. It is a localized space that stores only the exact ingredients, tools, and instructions needed to execute an incoming order instantly. This diagram maps the architecture. At the base is the device edge, sensors interacting with the physical world. Above is the on-site edge, applying real-time data filtering. At the top is the cloud, reserved strictly for heavy business logic. The edge is not one specific location. It is a distributed spectrum of processing layers, physically positioned to solve the rigid constraints of time and space. Engineers are driving this architectural shift across 5 strict operational vectors, which we can organize into the BLERP framework. The B stands for bandwidth optimization. Pushing 100% of a sensor's raw noise upstream to a data center creates a severe network bottleneck. Take a modern wind farm. By deploying a hybrid edge cloud system to manage their turbines, the volume of data transferred dropped by 96%. Local edge nodes analyze the raw video and sensor data right at the base of the turbine. They filter out the useless noise, like hours of empty sky, and only transmit high-value anomalies, like a mechanical fault, to the distant cloud. The L stands for latency reduction. This is critical for applications where the physical delay of a network round trip is completely unacceptable. In automated manufacturing, heavy robotic arms operate at immense speeds. They need sub-millisecond response times to detect anomalies and stop before causing catastrophic equipment damage. By positioning the computer logic directly on the factory floor, the system cuts out the wide area network transit entirely, allowing machines to react instantly to their environment. If you're finding this breakdown valuable, make sure to hit that subscribe button. We're decoding the complex tech of the next decade every week, and you don't want to miss what's coming next. Solving bandwidth and latency constraints enables a level of real-time physical automation that was previously impossible. The E stands for economics. Moving and storing zettabytes of data carries a staggering financial cost for any enterprise. This chart shows the financial impact on that same wind farm. Running a cloud-only system cost them over $80,000. Switching to an edge cloud hybrid model slashed that cost to under $29,000, purely by reducing data transmission. The financial math is so compelling that research firm Gartner predicts by 2025, 75% of all enterprise-generated data will be created and processed entirely outside of traditional centralized data centers. The R stands for reliability. Cloud-dependent operations are fragile. If a remote server goes down or a fiber cable is cut, the entire local operation stops. Local edge nodes and programmable logic controllers, or PLCs, which are specialized ruggedized computers used for industrial automation, solve this by maintaining operational autonomy. If a smart factory loses its internet connection, the local edge nodes ensure the plant doesn't blindly crash. The machinery either continues operating safely on local logic or executes a systematic, controlled shutdown. Decentralizing the compute architecture protects bottom-line revenue. It slashes exorbitant data egress fees and eliminates the cloud as a single point of failure. The final vector, P, stands for privacy and security. Moving massive datasets across public networks inherently increases a system's attack surface. It leaves data vulnerable to interception, or distributed denial of service, or DDoS attacks, where malicious actors overwhelm a network with flooded traffic to force it offline. Edge devices act as a secure filter. They can process video feeds and strip out personally identifiable information, like faces or license plates, before that data ever hits the public internet. Keeping this data processing strictly local also helps enterprises achieve compliance with rigid data residency laws, like Europe's GDPR, which strictly dictates where and how citizen data can be stored and moved. The BLERP Framework establishes edge computing as a mandatory architectural defense mechanism for the modern enterprise. A common misconception is that the edge will kill the cloud. In reality, the edge just forces the cloud to evolve its specific role, particularly in machine learning. The cloud's primary function is now aggregation and training. It takes massive historical datasets and uses huge server farms to train heavy, complex deep learning models asynchronously. But training a model is different from using it. The actual execution of a learned AI model in the real world to make a decision is called inference. Once a complex model is trained in the cloud, the resulting lightweight API endpoint is pushed down the network to resource-constrained edge nodes for real-time inference. An API, or Application Programming Interface, is a software intermediary that allows two separate applications to communicate with each other. This deployment routing shows logic originating in the cloud, pushing down through network elements to localized edge servers. Those servers then drive the instantaneous actions of end devices and sensors in the field, like smartwatches, robotics, and cameras. The cloud is optimized for learning across a global fleet over a long period of time, while the edge is optimized for acting in the critical millisecond. Which brings us back to the frozen highway, the autonomous vehicle, and the pedestrian. With an edge architecture, the vehicle's LiDAR isn't sent to a distant server. It's instantly routed into a hardware module bolted into the chassis. LiDAR is a sensor method using pulsed lasers to measure exact distances and map 3D environments. The local AI inference model processes the geometry on that internal board. It triggers the braking sequence in a fraction of a millisecond, and the pedestrian is saved. Simultaneously, the car executes a secondary action. It sends only a tiny compressed metadata packet up to the cloud, a simple text log noting a collision was avoided at a specific coordinate, to help improve the global fleet's algorithm for tomorrow. Next-generation infrastructure relies on a decentralized, federated network of intelligent nodes, pushing compute power to the absolute limits of the physical world.